Okay, so welcome to today's partner expert session. My name's Sophie Cramhoft. I'm going to be the host today, and together I've got Duncan and Chris with me here. So today's partner expert session is on Anaplan's calculation engine. So before we go into that, I just wanted to share with you a couple of other points on some upcoming events that we've got, some dates for your calendar. So the next partner expert session is going to be on Thursday, the 7th of December, and that's the one in January will be the topic of ALM on the 11th of January. We're also continuing our series of partner all-hands sessions where we cover our more strategic messages and some of the initiatives that we have going on, and that's going to be on the 21st of November. So the other big announcement that happened was that we made a new partner community. So I'm going to touch on that in a minute because I want you all to register. But before that, we have the platform release that's coming out on the 18th of November. So you should have received an invitation to a webinar that's both for you and for customers that's happening on the 17th of November. And here's some of the key features that are going to be covered in the release. So make sure, if you haven't got the invitation, you can also put it in the chat and I'll make sure that you get that so you can register. We want to make sure that you're informed at the same time as customers, so it's really key that you can learn at the same time there. So as I mentioned, we've launched a new partner community. So you may be familiar with the one on the left-hand side that we've had for a while now, but we've moved all the partner information into the same place as all our other information, which is the Anaplan community. So there's a new partner section here. And some of the key features that we've got in there is that we've got onboarding, content, enablement certifications, selling material, topics on delivery and customer success, all the events that we have going on you can find there. We've also got lots of marketing messaging. You can find the Anaplan partner logo, as well as latest news. So if you haven't registered yet, if you haven't seen the new partner community, this is how you access it. So if you've already got community access, you just need to have a partner access added onto that. So just let me know your username or send an email to support@community.anaplan.com. Otherwise, if you haven't ever been onto the community, I highly recommend it because we have training information, Anapedia, lots of content, and so click on register. Anyway, so moving on to today's topic, I'm really happy that we've got Duncan as a speaker here because he oversees both the design of the product functionality and its implementation as a cloud service. And he works really closely with a product management organization and a team of specialist software. He's been designing and implementing software for over 30 years. So I'm going to hand over to Duncan now. If you have any questions, we are going to pause during the expert session today to take those questions. So just put them in the questions section, which you can see there, and we'll make sure we get everything answered. So over to you, Duncan.
Thanks very much, Sophie. Hi, everyone. So as Sophie said, we're going inside the Anaplan calculation engine. Anaplan is a means of producing quite rich information systems for your customers. But at its heart is an in-memory database that does all the calculations and implements the business logic, and that's where we're going to go today. So I'm going to cover three main areas. The first of these is how data is laid out in the engine, and the reason for that is it gives some background into how some of the calculations work, and also into some of the performance characteristics which you'll find interesting. We're going to cover some aspects of the actual calculation mechanism itself, in particular the difference between what we call full calculation and selective calculation. The full calculation being all the data when you load the model, and selective calculation being keeping it. Manage multiple users coming in and reading and all writing at the same time and presenting consistent data to everyone, regardless of what anyone else is doing, while maintaining a reasonable throughput of change. Okay, so the first section, the data structures. So in the engine, we have these things called blocks, and basically a block corresponds to either a line item or a property. And essentially properties behave pretty much exactly like one-dimensional line items. So wherever I'm talking about blocks, if you think line items, that's not too far from the truth. It is a bit more complicated, and I'm going to come to that later. But for the moment, let's just think line item. So for instance, in this example, classic revenue is sales volume times price, then that would be represented by 3 blocks in memory. Okay, so when you have a line item and it has an applies to, that applies to specifies 3 lists, or however many lists, in this example, three lists. But it's not just the list, because each list has a parent hierarchy going up from it. In this case, in the example I've chosen, sales volume might vary by region, product, and channel. And region would have 4 levels, product maybe 3 levels, and channel 2 levels, just like this. And I count the top level item as one of those things. Now, as you look at the data from within your browser, you can look at it at any level of aggregation. So you could look at it city by product, by all channels, or region by SKU, by channel. So with 4 region levels, 3 product levels, and 2 channel levels, that's a combination of 24 different ways of aggregating the data. And we actually pre-calculate and keep up to date all 24 of those, and each of those is a block in memory. Okay, so when I talk about a block, it's not just a block for the leaf level line item, but it's also a block for every possible aggregation combination. And when you open the line item in the browser, you see, if you have your totals after, you see all of those merged into the same view, but in the underlying engine, they're kept separate. So just a diagram of this. The green represents the leaf data, so Q, and these are all the aggregate blocks. So we've got the aggregation up the region hierarchy, the aggregation up the product hierarchy, and then if you look down through the kind of pages, the aggregation into the channels hierarchy. And if you look at this little bit here, that is actually just a single cell block, and that's all products, all channels, all regions. Okay. When we aggregate along one dimension, starting with region, and then up through the product hierarchies, and then down across from channel to all channels. So just like this. Okay. So what does that block actually look like in memory? Taking a slightly simpler example, the 2-dimensional example, in this case region by product, you think of it as a grid, but the way we lay it out in memory as a continuous sequence of numbers. So as it is down here, so this is the same sequence of numbers. So the top line, then the next line, then the next line. And when you ask for a particular one, we look at the rows and columns of that and we translate it into what that means. We do some index arithmetic and we translate it to what that means as an index in what we call the raveled structure. Okay, so in this case this is index 2 and this is index 1 and this is 4 long, so it's 1 times 4 plus 2 gives us 6, which gives us that one. Okay, so any questions on the data structures?
Duncan, we have one question that came in through the chat. I've always put top levels in all of my lists. Is it a best practice to only make sure that we need it for any list that needs to have any sort of aggregation within there?
So one of the things about top level is that, first of all, if a list has a parent list, then top level is meaningless in that list. It's only if a list doesn't have a parent that top level actually has any effect. And there can be lists that it's useful not to have top level in. If, for instance, if the things in the list shouldn't be aggregated, such as their scenarios, then if you don't have a top level, then anyone that tries to do the calculation, the engine will complain and say, I'm sorry, you can't look at it at the top level because there isn't one. So it's a kind of checking mechanism. But in the normal case, I would put one, yeah. Because you never know, if the data is aggregable, you never know when you're going to need that top level. Okay? Right, moving on to the calculation.
All the questions we have in the chat.
Okay, great. Moving on to the calculation mechanism. So when you write a formula, you make reference to other line items. And basically what you're doing is you're creating a dependence from the line item that you write the formula on to the line item that you reference in the formula. And that creates that dependence between the blocks, so that if something changes in the upstream block, then you need to recalculate the downstream block. So we take these dependencies and we form them into what we call a directed acyclic graph, which will be familiar to anyone who's done computer science. But if you're like me, then it's don't worry about the term. But basically, it means that each connection has a direction, so a dependence from something to something else, and that there's no circularity. And you probably come across quite a lot trying to do some calculations, and it comes back and it says you can't do this because that would be a circular reference. And because we don't have circular references, we can have this directed acyclic graph. And it does give us a couple of things. One is that if you change a particular line item, we can just look at this graph and we can determine all the downstream blocks that change as a consequence of that. So the other thing is that when we're doing the calculations, we don't have to put in any special code at calculation time to check whether we're in some continuous loop or not. Loop detection actually slows down your calculations quite a lot, but because we've checked up front that there are no circularities in those calculations, we can just go straight ahead and crack on with the calculations themselves. And finally, we can execute independent block calculations at the same time. And the servers that we run on have multiple processors, and each with multiple cores. So between 64 and 144 different tasks can be running concurrently. And of course, that's only if they're independent. So here's a quick example. We're extending the revenue example by adding unit cost, which means that we can have cost of goods sold. With cost of goods sold, we can determine profit and margin percent. Okay, and if we look at a diagram of this, then on the left we see the detail data, and these are the edges of the directed acyclic graph, and these are the calculated blocks. So you can see that if we change price, then immediately we know that it's revenue, profit, and margin percent that we're going to have to update. If we change sales volume, we're going to have to change all of them. Now, you can see from this that these two blocks are independent, so they can be executed concurrently. However, the calculation for this sits in a layer by itself. So you would think that when we're executing profit, recalculating profit, then we're not using all the power of the machines. We're not using the concurrency of the machines. However, because every single cell in this block only depends on cells that have already been calculated and doesn't depend on anything else within the same block. Effectively, each cell is independent. So what we do is we take the block and we split it up into sections. We don't actually move anything around. We just logically identify different sections, and we have different tasks recalculating the different sections at the same time. So even if you only have one line item, one block being executed at a particular time, we're still getting that parallel, that concurrency. Okay. So at the beginning, I referred to two different calculation modes, and first of those is full calculation. And characteristic of Anaplan that sets it apart from quite a lot of other tools of a similar nature is that when you define calculations in your model and when you have aggregations, we pre-calculate all of those numbers and we have them ready so that no matter what query you make, no matter what numbers you read at any level of aggregation, no matter what's gone into them, they are all calculated and ready to serve up. So when you're just reading opening dashboards and stuff like that, the performance is good no matter where you go in the model. Now, when you start up the model, we only have the detailed data, and so full calculation is how we get to that completely loaded state. Selective calculation is what happens when you change data. So if you change a particular cell within a line item, we're not going to recalculate all of the cells in the downstream line items. We're only going to recalculate the ones that have actually need to change. This is the normal mode of Anaplan when you're typing data in, and this is basically minimal recalculation. So full recalculation, we showed you the block as a sequence of numbers, and what we do is we take the block being calculated, the downstream block, and we walk down those in index order from 0 down to the full size. And for each one, we go to the corresponding cells in the source blocks. So if we were calculating revenue, we'd go to the corresponding cells in sales volume and corresponding cell in price. We read them and then we do that calculation. And in the majority of cases, they will be in exactly the same order as the block that we're calculating. So index 5 will be reading from index 5 and so on. And this has a particular effect. The majority of the time that the computer spends doing all this stuff, doing anything in fact, is reading data from memory onto the chip and writing it back to the main memory. That's orders of magnitude more expensive than actually doing the calculations. But if you read the memory in a particular sequence, the processor notices that you're reading in a particular sequence, and it fetches it in advance and it puts it in a thing called the cache, which and so as we're traversing these blocks in index order, then we get a probably more than 10 times speed up on our memory access, and that basically translates into considerably faster calculations, which is how we can get away with pre-calculating the entire model as you load it. Okay, so this is just a diagram illustrating that. So we're walking down revenue in order, and we're reading the corresponding cells from sales volume and price. Okay. Now, an interesting thing comes out of this. if you look at a blueprint and you look at the applies to on a blueprint, you see that the lists in the applies to are basically just comma separated, and you can select them from the dialog, or you could just type them in, and it would be possible to take one line item and type them in one order, and take another line item and type them in a different order. And this is what you get when you do that. Let's say we've done that for sales volume and price with the region. This is exactly the same stuff that we had before, but you can see that everything's mixed up between the two. And if we actually draw the lines between them, so as I'm walking across revenue, it's either going to be in one order or the other. So it's either reading in sequence from sales volume, or it's reading almost completely randomly from price. And as it's reading completely randomly from price, then the processor looks at it and says, I haven't got a clue what you're doing. And it can't do any prefetch. So everything slows down. And I've done tests in Anaplan, and I've seen about a factor of 5 difference on a reasonably large line item for simple calculations when they're in the wrong order. So this really is something to watch out for. It almost certainly you won't have it, because if you pick your applies to from that dialog where you just pick them from the list, they will come in the correct order. Okay. So selective recalculation, this is what happens when you change a single number, or you change 2 or 3 numbers, or you have 5 or 6 different people, or however many changing individual numbers. So when you make a change, we store the index of that change in another data structure next to the block called the delta. And we store up to 1% of the size of the block we store as changes. And when we're recalculating a downstream block from there, we read the delta indices from each changed upstream block. And we look at the upstream indices and we say, okay, if that particular index in the upstream block has changed, that means that these indices in the downstream, in the thing I'm calculated, need to be recalculated. It goes off and it recalculates those. And I've got an example of that later on that I'm going to show you. So, and when it recalculates those particular cells, it checks to see whether the result is different from what was already there, and only if it's different does it store that index in its own delta. Okay? And if we go over 1%, we basically say the whole thing has changed. Now, that if one of those upstream blocks has got this, everything has changed in it, then the target completely recalculates. But if less than 1% of the target actually change, then everything downstream of the target can still do selective recalculation. So you might get a block of full calculation in the middle of a sequence, and then for it to revert to selective recalculation. And one of the things that the analysis that Hypercare can give customers is to tell exactly what's happening with selective recalculation and full calculation and the like. Okay. So I talk about taking source indices and determining what in the target has changed. And I also talk about for a particular target cell, working out what source cells feed into it. So we keep data structures called correspondences, and they're basically needed every time there is some kind of dimensionality change, such as in aggregation, or where the relationship between the source and the target is complex. So a sum or a lookup, for instance, is one example of that. So a correspondence has two sets of indices. It's basically a two-way lookup. So we have source to target, and that means when a particular source index changes, we can work out what downstream target indices change. And target to source, which says when I'm calculating a particular target cell, these are the source cells that I need to go to. So take a simple example of that. So this is a one-dimensional line item with aggregation. And I have on the right the correspondence for the relationship between the country block and the city block. Okay, so let's say I change city at index 5. I walk down to 5, and index 5, and I see it's 2. So I go and update 2, and in updating 2, I need to read 4 and 5. Okay, so then I've changed 2, that goes to 1, and so on. And you saw at the top, for all regions, it reads every cell from the level below. And this is another case where it explains some slightly odd behavior that you might see. If you have a particularly long list, so millions of items, and it doesn't have a parent list, but it has an all, then if you change for every single thing that you change on a line item that has that list, it's reading the data for every other line item in order to add up into the all item at the top. That means that selective calculation can actually be even slower than full calculation for that particular block. And you can alleviate that by putting an extra level in between. Even though you might not look at it, and you might have to remove it from your views and stuff like that. But that's just a little kind of performance trick if you find yourself in the situation with only a top level item. Okay. So I said pretty much at the beginning that a line item was a block, and I said that that wasn't quite true, and this is the explanation for why. Anaplan has very good support for time calculations, and it has a built-in time dimension. And you know, in financial situations, there are a lot of circular style calculations that are circular at the line item level, but not at the period level. So this is the classic one: opening balance, closing balance from the previous period, and closing balance is opening balance plus income minus expenditure. So what we do is we actually say it's not a block per line item, it's actually a block per line item period. And if we draw that out, it changes it from being a circle into a spiral. Okay? And that's how we get around the circularity in time calculations. And this is particularly true of previous, next, moving sum, and we've recently had some improvements to lead and lag to make them have this characteristic that they respected this breaking up of line items into multiple blocks over time. Okay. Any questions on that?
Duncan, we have one question. Is there a way to see how many calculations a formula is dependent on? And is there a number that we should say at that point to change?
There isn't at the moment. We are looking into tooling to make that information available. There there are interesting things that you can bear in mind when you're doing calculations. One, if we go back, sorry, this is quite a long way. If we go back to here, this is something that can improve performance but reduce readability. So I can define profit as revenue minus COGS. I could also define profit as sales volume times price minus unit cost. And if I did that, then this would only be referring to these and could come back to here and be calculated at the same time as these. So you get a more complicated formula, but you get more concurrency. That's sometimes a way in which you can improve recalculation performance. Does that make sense?
I'll wait to see if they respond. And then there was one more question. Can you give a better example of when you would want to put in a middle level?
So, better example. Can't remember the exact. I've seen this in a model that's got performance problems at the moment, and I'm trying to remember whether it was SKUs or accounts, or no, it wouldn't have been that, because they naturally have extra levels. I think it was something like some kind of transaction list that had an all, but it didn't actually have a top level, and the list was 10 million items long, which basically means that if you let's say we list is 10 million items long, and we have a line item that varies by that list, and maybe another one that's 100 items. So in order to, when you change an individual cell, it's reading 10 million other cells in order to add up, in order to get to the top level item on that list. If I put in another level that maybe had 1,000 items per parent, then when I change, so let's go to that this example. Let's say this was 1 million, this is 1 million, and that's just the one. When I change one of these, calculating that has got to read all of them. If instead I put this in place that has 100 children per parent, and this has 100 of these per parent, and this has 100 of those per parent, I've still got the same million down here, and it's still feeding up into the same zero there. But when I change this, I'm reading 100 to calculate that, another 100 to calculate that, and a third 100 to calculate that. So instead of reading and adding up 1 million numbers, I'm only adding up 300. Does that make sense?
Yep. And also the other one question the answer made sense as well.
Okay, great.
And that's all the questions we have.
Okay, so right, next section is maintaining consistency and throughput. So Anaplan has many users interact. An Anaplan model typically have many users interacting with it at the same time, particularly when it's coming to quarter end or whatever. And they can enter data and they get back the results of their data and also anything else that anyone else has entered at the same time. But what they see is always completely consistent with respect to the calculations and the aggregations. So wherever you see a total of children, the children will add up to the total correctly. Wherever you see calculated item and the things that it was calculated from, it all works. And we put a huge amount of effort to making sure that's the case. Okay, so how do we do that? So we have all the requests, they come in, and we have a Java process sitting on the server holding your model in memory. And that Java process has a number of threads that are taking requests. And they put those requests on a queue, and we have a single request processing thread that runs in a loop, taking stuff off the queue and processing it. And it processes it, it uses all the multi-threading capability that I was talking about earlier to process it as quickly as possible. So there are 4 main phases to each of those loops. If there's any restructure work to do, so for instance, if an admin has been in there and has changed the applies to on something, or if a list has increased in size, or you've added another version or whatever, then that restructuring needs to take place before anything else. And part of it, if you've changed a formula, for instance, it needs to recalculate that directed acyclic graph. So when that restructure has happened, then we can go in and we can do data change. So the particular cell changes that have happened go in, but you can actually have multiple cell changes from individual people. Provided they don't hit the same cells, we can process them all at the same time because they're all going into the detail blocks. And then we recalculate all of that. And once it's all recalculated and it's all completely up to date and consistent, then we do all the reads. We let the reads in. And as I said before, we don't have to have any locking between the read and the write because we just separately segregate them. Okay? So we block, but we are multi-threaded. And we don't have any internal locking, which means that the stuff that we do works faster. And we segregate the read and the write. Okay? And then, when we've done that and we've read the data out, that data gets processed into a response that comes back up to the browser. And that response generation is actually done on the other threads, which are not blocks, so they can all run concurrently. So if you look at the changes that an individual client, individual browser can make, they fall into 3 main categories according to whether you're changing something about the model, you've been on the settings tab, or you're just typing in data, or perhaps you're just requesting new data for a grid or something like that. Now, every request will contain queries because whatever you're looking at, it needs to keep up to date, which is why you see a view request in all of these. But some of them will have data changes, and some of them, very few, will have model changes. And so we categorize the entire request by whether it's got a model change, a data change, or just a view. And we keep them on a queue, and we put all the views at the front of the queue, and we put the rest higgledy-piggledy at the back. And when we're doing the processing, when this request thread is looking at them, it takes all the read requests, because they can all be done together. It takes as many non-overlapping writes, cell writes, as it can find, so that's these ones, and then it stops at the first model change, because only one of them can be done at a time, because working out whether individual model changes are compatible is too much for even our brains to handle. So we put a marker on the queue and we say, okay, we're going to process that lot. We'll process the model change first, And while we're processing it, there's probably a lot more happening. More users are making requests, so their requests are coming in. The read requests, the pure read requests at the front, and everything else at the back. And we process the data, and then we process the views. And okay, so we're now going to go back to a new run. And if we did what we did before and we came to here and we processed that model change and then these and then that, these guys, the ones who've been basically just paging down a grid or whatever, they're actually going to have been waiting quite a while. So we just nip in and we do a quick reads only loop, and then we get back to normal processing. So we have this process read cycle. So the model is always basically either doing processing changes and then doing reads, or just doing pure reads. Okay, so that's how we keep consistency, and that's how we keep a good throughput. Any more questions?
So one question how can we use this knowledge to help our performance? And this was just around the last section there.
So I would definitely segregate users, the use case of doing reads from updating data, and definitely just reading dashboards where all you're doing is opening the dashboard, interacting with, and basically scrolling around the grid, selecting new pages and stuff like that. They will get treated with much better response than stuff where you're changing data at the same time. In that every other cycle, it does that quick response, get all the reads out of the way. And the reads are considerably faster than doing data change and recalculation. Okay.
Yep, just one. So you're saying that we should have dashboards that are read-only and then dashboards that are separate for inputting data?
I'm saying that read-only dashboards will perform better.
Sounds good. Okay, I think that's, any more questions from anyone else? All right, Duncan, looks like we have no more questions here.
Okay, well, thanks very much for coming.